Well, welcome back, everyone. Looks like it's official. We can get started. So we're now on week 11. We're just about done with section 11.5, and we'll be moving into the ratio and root tests right after. Any questions at all, folks, to start us out today? Okay, I do notice I do have a small problem on my Moodle website. I want to move this document to the very bottom. I think I just forgot to do that today. This document right here is pretty much just coming along for the ride. Summary of tests for series. And we just about have everything on here that we're getting through. Let's park it right down here for the moment. Okay, we'll call up that file just as soon as we need it. And now we're just about done with section 11.5, but we ended up leaving this on a place where the next set of questions are more technical than normal. This is where a lot of our tests kind of start to go together at once. So you know what, might be a good idea to also pull this out just for quicker reference. So I should have done this before class, but you know how that goes. You always kind of forget the little things. So here is our summary of tests for series. Just want to zoom in on it. We'll be using these quite a lot as we go through our next questions. But just as a refresher, because it's a more technical topic, let's go through absolute convergence and conditional convergence once more. When we say something is absolutely convergent, a series like this one, what we mean is when we put absolute values on each of the terms individually, so this right here, we're getting convergence in that kind of way. So that's what we mean by absolutely convergent. It converges when you put absolute values on all of the terms. And sometimes you can get things where behavior is unexpected. This series right here by the red dot is the convergent alternating harmonic series. And we showed it converged up there on the notes. But if you put absolute values like this on every single one of the terms, here's what happens. Alternating harmonic series is no longer alternating. We've wiped out the -1 power n portion. And now it's the divergent harmonic series. That means the series converges conditionally. Again, what we mean by that is the original series converges. That's what happens on this line. But when we took absolute values of all the terms, it diverged. That's what happened on this line right here. So we call the whole thing conditionally convergent. One way to think about it is it's convergent on the condition you didn't do that, put absolute values on every single term. But the bigger story here is we now have an honest-to-goodness trichotomy and a brand new test at the same time. This is the absolute convergence test. It's extremely powerful when used for the right kind of series, and it's kind of an awkward series in all the other times, but we'll find some good use for it in these notes. The absolute convergence test says, pick any random series like this one, and if you do put absolute values on it, and it happens to converge, then the original series itself was a convergent one from the very beginning. We say it converges absolutely. Then, in our definitions, we have the trichotomy. Any series you put down on paper, anything whatsoever, can do one and only exactly one of the three. It could converge absolutely, converge conditionally, or it could diverge. And by the way, there's a really short blurb at the very end of the section 11.5. It's kind of technical, but it's just a really quick write-up. I encourage you to read that last part because conditionally convergent series are pretty bizarre, a lot more bizarre than we would expect. We still say that they converge, but what they converge to is kind of a different matter after looking at that write-up. Absolute convergence is more along the lines of we really do have an honest number and only one number that represents the total number of the series. Well, any questions, folks, with the refresher on these concepts? Okay, they're all pretty tricky, so really the best way to kind of absorb this, look at particular examples like we did here, and do the examples. So let's give this a try. We'll determine if the series is absolutely convergent, conditionally convergent, or divergent. Watch out for these kinds of instructions because it always says this is a longer problem than we might have expected. So if this was an exam problem, probably the last one on the paper, and you have lots of extra space to put down your thoughts. They'll say, give a conclusion divergence for all series tested. We're going to deal with more than one series is what this is trying to say. And for every test or convergence or divergence, we have to state the name, show all steps. Really the same stuff we've been harping at before. So starting off with this one, well, we're going to determine where does it fit in A, B, and C in this dichotomy. First thing to take away about it is it does alternate. It has -1 to the power of n. And in this section, we have the alternating series test. So that probably is a good place to start. Let's just call out our test right here. Alternating series test. In the alternating series test, we need a brand new series. We come from here and we say summation Bn is going to be the summation as we go from 1 to infinity. And essentially, this is what we're thinking. We're getting rid of that part, the part that's alternating, and we're just going 1 over. Let me fix the color first. 1 over. The fourth root of n cubed is just n to the power 3/4. So that's our related series. But in the alternating series test, we do 2 additional things after we define that new series. Step 1, we have to show or argue that Bn is a decreasing sequence. Looking at the form of Bn, that's plausible. In fact, it is absolutely decreasing. It starts at 1, and the numbers, as we get larger and larger values of n, just give us bigger and bigger values in the denominator, and so the whole thing gets smaller and smaller as n increases. So step 1 works out for us. The critical step now in the alternating series test is we're taking a limit, and we want that limit to be 0. Notice already how kind of confusing that is. There's a test for divergence. We want that limit to be not 0, so we can give a conclusion of divergence. But if we move over to the other test, in the alternating series test, we want the limit to be 0 so that we can give the conclusion of convergence. These are really finicky tests. Alternating series only gives a test or a conclusion of convergence, and test for divergence only gives a conclusion of divergence, not convergence. So keeping these things separate in our mind when we're looking for equal 0 or looking for not equal 0 is super important to get all these kind of series tests working out. So let's take our limit and hope for a value of 0. That should totally work out, right? If that's the form of our terms, then we can say limit as n goes to infinity. Forgot to use color coding right here, so let's just slap it with a highlighter. Limit as n goes to infinity of Bn is the limit as n goes to infinity of 1 over n power 3/4. This has a limit of 0. Since it has a horizontal asymptote at 0 with the denominator growing without bound, so because of conditions 1 and 2, we can say that this thing, here's our big conclusion, summation an, that looks like a Q, let me fix that. Summation an, more specifically, as we go from 1 to infinity, -1 power n, so now we're bringing in the alternating part, fourth root of n cubed, converges. So that's our very first step. We found convergence of this series, but that just means we've eliminated that possibility, and we need to find out what type of convergence. Let's put this on the notes just to convey what we're doing next. I mean, it already is on the notes, but let's make it an official screenshot. to carry on our next thoughts. First, any questions, folks, on running through the alternating series test? Okay, so because of the instructions, we're looking for 3 different kind of outcomes. Let's place that there just as a reminder. And I think we're going to need a next page. Let's just say here, continues. We need to find the right kind of convergence. So it's either converging conditionally or absolutely. The only way to resolve that is we're going to take the absolute value of all the terms of this series. So it starts off like this. Summation an in absolute value, that's our new series to analyze, goes from n equals 1 to infinity, summation, absolute value, -1 to the power of n. Instead of writing the 4th root of n cubed, let's just go right to the punchline. That's n power 3/4. The absolute value right here is just going to bring us back to that series, but let's just write it in. It's now summation. N goes from 1 to infinity of 1 over n to the power 3/4. So we need to test this for convergence divergence. Any volunteers for what the outcome should be on that one?
Is this a P series?
Yeah, absolutely. Good call on that one.
And forgive me, I forget, but like if R is, or if P is less than 1, I forget if it converges or diverges, but
You're on the right track. Less than or equals to 1 is our conclusion for divergence in this case. But yeah, that's awesome. That's pretty much the major thing, is knowing what series it is. Imagine this is a real exam question. The moment you do know it's a P series, you would just go to a document like this one, look up the relevant information, and we're in this land, less than or equals to 1. So this is pretty much
yeah,
the
that's what I'm
experience.
kind of banking on.
Gotcha. Yeah, that's the part that you would be just fine on in a real exam situation. So from this part right here, we'll say diverges. Well, we have found that this part diverges. That means we have eliminated this possibility. It cannot converge absolutely because when we put the absolute values on, we got divergence. If we said convergence right here, we would have said converges absolutely. But here we are in this case. It's conditional convergence on this series. We have to give that final conclusion. We'll say, therefore, summation an. Now we're talking about the original series. Let's just write in just to be specific. We don't have to do that in your notes, but as a paper trail, let's write it this way. So this series right here is conditionally convergent. That's a long word. So if you decide to write COND for conditionally, CONV from convergent, those kind of shorthands are totally fine. Reasonable and almost expected in an exam setting where you're saving time. Well, that's our first one down. Again, they're pretty long problems, but also take a look at how many tests we actually used. We used the alternating series test, so that's 1. We used the P series test, so that's test 2. We didn't use the absolute convergence test right here because we never called to it. It wasn't absolutely convergent in the first place. So this one took 2 tests to navigate through, 2 different series. Any questions or comments so far, folks, getting through that one?
Had
When
it
you
converged absolutely, we would have had to do the absolute convergence test, the third test.
Yes, so you're referring to this one right here?
Yes.
Yeah, exactly. So if we just start off with that, and it turns out it converges when we use that test, we just stop and say, converges absolutely. There's no further work to do at that point. Other questions with that one?
when you took the absolute value of an, why didn't the power n on the numerator follow?
Follow to the step right here.
Oh, never mind, never mind. I understand. Mine.
No worries. Other questions at the moment? Okay, another thing to make as a comment on this, the order that we did this problem is not too important. Let's actually say this right here. It's a confusing enough problem to give a little bit more post-analysis. You can either start with summation absolute value an, and if it converges, then the whole series, let me move that way down, then the original series, summation an, is absolutely convergent. But now the downside is if summation an diverges, then that does not actually mean the original series diverges. It could be that this is conditionally convergent. And so what we have to now do is we must use another test on the original series summation an. So the order you do it is not important. We started here. We tested the original series an and found it converged. And so we wondered, will it converge absolutely? So we did this as our last step. And the problem we just did, if you started here, you would have gotten divergence, and then you would have had to use the alternating series test when you go to use the other test portion. So either way you put down your results makes no difference. You come to the same exact conclusion. I would say for generic advice, if you're looking at just a random series like this one, and you're not too sure where to start, just analyze what test seems to make the most sense and go right there as your starting point. I think most of the time, that's going to make the work a little bit more streamlined. Well, any other questions or comments, folks, before we try another? Okay, let's give this another try then. So we talked about a series. Oh, I guess there's a couple more. That's exciting. We'll put that one on the next page. We talked about this series a little bit. Cosine n is really tricky in that as a series gives you terms which do not alternate. It's kind of surprising. You would need cosine n pi to make this alternate. Think of your homework in section 11.1. So the first thing to note about this is not alternating. Some terms are positive, some terms are negative, but it doesn't go positive, negative forever. Sometimes it doubles up on the negative terms and the positive terms. That means we can't even use the alternating series test on this. It's totally out of bounds. But we can still do something. Let's maybe mention you can do these kinds of things out of order. If you're not too sure how to even start this one, let's start this way. Absolute convergence test. The absolute convergence test means we're taking this original series, let's give it a name by going equals summation an, or putting absolute values on the individual terms. So it's going to look this way, summation absolute value an. That's pretty much how the absolute convergence test starts, just writing down that symbol. If you don't write down that symbol, you're still going to write down this symbol eventually. Summation as n goes from 1 to infinity, absolute value of cosine n, divide by 4 to the nth power. Now we can simplify the absolute values a little bit. For example, 4 to the power of n is always positive in the denominator, so absolute value bars pass right through it, but they center on cosine n, where we can't actually drop them. It's summation n goes from 1 to infinity, absolute value of cosine n, divide by 4 to the nth power. So that's the formula that our series takes in the absolute convergence test. And again, absolute value of cosine n can't be dropped. You need to know the value of n, whether it's positive or negative, to do anything further. So it's stuck right at that step. We need to test this out, but to test this, we need a whole different test. Here's one hint though. It's all about cosine n. We know one great estimate for cosine n is that cosine n, no matter what, less than or equal to -1, bigger than or, let me say this a little bit more cohesive way. Bigger than or equal to -1 is the way you say it, and less than or equal to +1. That's kind of embarrassing. The positive should be on this upper end here. So if we take the absolute value of this whole thing, this implies absolute value of cosine n is less than or equal to +1. If you can make an estimate like that for, say, the numerator in this series, that means the next natural test is the comparison test. Not the limit comparison, but just the ordinary comparison test. This is actually a really, really good matchup for that one. So let's now go and say comparison test. We're calling out the test right as they're being used so that we just don't forget that step. In the comparison test, we have this estimate. Summation an equals, and it goes from 1 to infinity, summation cosine of n divided by 4 to the power of n. We estimate right here, and we're going to plug in a 1 in that place for the numerator. That means we're going to put in a less than or equals to, and goes from 1 to infinity, 1 over 4 to the nth power. So in the comparison test, if we suspect that this is converging, then we need another convergence series. But right over here, that's a third test we need to put down. Anyone happen to know what test applies to the new series there by the red dot? Yeah. Absolutely, good call. This one is now a geometric series. Let's move on to a new line just to put it in a more natural format. We're going from 1 to infinity. And you could put a power n on 1, so it's 1 to the nth power. So the whole thing becomes 1 over 4 to the nth power. This just helps us out with convergence or divergence. So when we're looking at the summary of tests, P-series is kind of similar here, except that in P-series, you want larger than 1 for convergence. And then when you go down to, where in the world did it go? It's got to be here somewhere. Geometric series, sorry, I was looking right at it. When you go to the geometric series, you want the absolute value of your ratio less than 1. Already, that's kind of awful in our minds. So watch out for that. That's convergence here. And watch out for, I lost it, the other one in P series. There we go. Here's the thought. So for P series, convergence happens when P is greater than 1. But for geometric series, convergence is when your common ratio R is strictly less than 1. Again, these are good to highlight and think about as you're going through these tests, because the more you can make sense of these weird directions, the easier it becomes to apply the tests. So last thing we have to say here is, well, we do need to say what test we're about to use. So here's another test. Let's write it out this way. R equals 1/4 less than 1. So converges by geo series. So I kind of abbreviate this one, geo and S dot for series. It's by the geometric series test, but you're always welcome to just shorthand. If I know that you know what the series is and when the test is, this is good enough for me. So let's unwind and go backwards. We're testing that thing for absolute convergence as our first step. So we put absolute values on it. Now we're kind of stuck on this series until we compare it to this one using the estimate for cosine. It became a geometric series and means it converged. But that's actually really important for the comparison test. The most important features of the comparison test are, if you are converging, you have to have less than or equals right here, because now the logic says our series we're interested in is smaller than a known convergent one over here by the geometric series. We get to make a conclusion and say, therefore, summation an converges absolutely. Here's where the problem finally ends. We began with the absolute convergence test, and through a couple extra tests all at the same time, we have a statement of convergence. That means we don't have to do anything further. This resolves the trichotomy. We set the type of convergence right away. Well, any questions at all, folks, getting through this kind of a strange problem? Okay, one suggestion I would have about doing homework is when you go to do homework, definitely grab one of these documents. Either this one, this is the one I'm using in class, just because the notation on that document is more common to the reading and the problems. Or grab this document if you like it as a flow chart. Just watch out for the slight differences in notation, nothing too major, but enough to make it look a little funny. Then just have these documents pulled up and ready to go, maybe just to your right, on every single new series you take a look at, because our real goal here is we need to be just fluent with everything that's on this, just in case one of these kinds of things come up. So now on the next problem, looks like something a little bit more gnarly, but we'll give this a try. I'll leave it up to the class. How would you all like to start out? It looks like it's an alternating series, so we can do that test or hit it with absolute convergence test. Any volunteers for a direction on this one?
Alternating.
I think that's a good call. This right here tells us it's an alternating series, and sometimes if you know the series, best to just run the test. We're going to have to anyways. So let's give this whole thing a name, summation AN. Then let's say let BN be equal to this portion, the part that doesn't alternate. It's 2n minus 1 over n cubed minus 3n. So once we have that, we show two things. The first thing we have to show, or really more just a statement, we have to know that this is a decreasing sequence. This is true. It's linear degree 1 in the numerator, cubic degree 3 in the denominator. So for large values of n, this total value of that term gets smaller and smaller. So we can say Bn is decreasing, and for step 2, we're taking a limit. Limit as n goes to infinity of the nth term Bn is the limit as n goes to infinity of 2n minus 1 over n cubed minus 3n. And this limit already has an immediate answer. It's a rational function in the variable n. And if the degree of the denominator is larger than the degree in the numerator, it's a foregone conclusion the limit is 0, because it now has a horizontal asymptote, y equals 0. But that's actually what we want. We need a limit of 0. Let's take a look at the test just to be really sure we're doing what we need to do. Look at that part right there. As soon as you get the limit of 0 on that decreasing sequence, you're in business. We can say it converges. And what converges is the whole thing. It's including the alternating part. So now we can say summation AN converges by alternating series. I'll just say alternating, S for series, test. But now we have two kinds of convergence, so we have to resolve which kind it is. It's either absolute convergence or it's conditional. Well, any questions first, folks, before we look into the type of convergence? Okay, let's take it to the next step. So for our next portion, let's apply the absolute convergence test. This is a little bit tricky because if you're looking at these terms, weird things happen when n is 1. For example, when n is 1, we have positive in the numerator, positive 1, but the denominator is 1 minus 3 for a negative 2. When n is 2, we have positive above and positive below. When n is 3, again, positive above and below. But it looks like when n is 1, that's a pretty exceptional case. It means taking absolute values on this series is a little bit tricky because sometimes the absolute values drop off, other times they stay fixed and we have a negative value. So here's one idea the author mentions occasionally in the reading. Convergence, divergence is not affected by removing finitely many terms. If the series diverges, taking out the first two terms isn't going to change that fact. It's still diverging. And if this is a convergent series, or this one right here, when we're doing the absolute convergence test with absolute values on it, then the convergence or divergence of that won't be affected if we take off again a few couple terms. So in this problem, just to make absolute values easy, start at n equals 2 to help with absolute value. So here's how our test is going to start off. In absolute convergence test, this is the new series, summation an. That's just the symbol we're using to describe the whole thing. Think of it like a variable x. But it means we're placing absolute values on that. So it turns into summation. We're starting at 2 again to make absolute values easy. We're going from 2 to infinity. Absolute value -1 power of n to n minus 1 and cubed minus 3 power n. So starting at 2 means the absolute values don't affect any of these terms. They're always positive. The only thing that affects is right here. It's just going to eliminate it. So we get a new summation going from 2 to infinity of 2n minus 1 divided by n cubed minus 3n. So that's our new series to analyze. Any questions or comments to this stage? Okay, well, we've got to test the convergence or divergence of that now. So that's the downside of all this. It looks like probably what would work the best if you see a random rational function with unfortunate signs where it makes it look like a comparison test might be a hard analysis. You want to go to limit comparison test. That's usually your next best bet for something that looks like this, a random rational function. So in limit comparison test, we need a new series Bn. But the way we grab it is we go to the numerator, and the most important term in the numerator is 2n. When n is large, that's the thing that's going to matter the most, and we only need the variable part, n. Likewise, in the denominator, the thing that matters the most is n cubed. So this suggests let summation Bn be equal to the summation as n goes from 1 to infinity of n over n cubed, which is the summation as n goes from 1 to infinity, 1 over n squared. That's kind of a nice series. This is a p series. Power p is 2, which is greater than 1. This is always a point of time to kind of reflect and make real sure. That's bad for a geometric series, but for a p series, this implies convergence right away. So we'll say converges. So taking a look at what we're doing so far, we're using the absolute convergence test right here, but in the middle of that, we have a complicated series. So we're over here, we're comparing it to a p series which converges, but we still have to say what test we're about to use. This is the limit comparison test. And the limit comparison test, the convergence or divergence of this right here is totally dictated by the fact that this one converges, but if and only if our limit comes out right. So we need a limit that's not 0. Let's go to the right spot. So we need a limit to come out as C, where it's positive. If it's 0, the test has failed. We need a different test. And it has to be finite. We can't get an infinity either. If that happens, then both series converge or they both diverge. We said convergence here, so if our limit comes out right, we will say both series converges by limit comparison test. So let's write out the limit next. It's limit as n goes to infinity of, let's take another look at that test. We actually don't say an anymore. And the reason is we're not using the original series, we're using that one. So just to be specific on what we're doing, we should say absolute value of an. It reminds us which terms we're really using. Let's use a little bit of color coding too while we're at it. So absolute value of an divided by Bn is how our limit comparison test is going to come together this time. So now it's the limit as n goes to infinity. Oh, and one small correction here. Sorry for pausing right in the middle. I forget we're starting at 2. And so that means this is starting at 2 as well. Let me just put it. I was going to X through that. Let me go this way. Equals 2 and equals 2 right here. Sorry for that correction. Those are always weird to deal with, but they're important to correct, or else the math just looks weird. So limit as n goes to infinity. First of an is this right here, 2n minus 1 over n cubed minus 3n. It's going to be multiplied by the reciprocal of bn, so that's n squared over 1. That means we're almost done with the limit. Let's put it together. Lim as n goes to infinity. In the numerator, it's 2n cubed minus 1. Denominator, it's, let's put a 1 times n cubed, just to be specific with the shorthand, minus 3 power n. Next, to do the limit, we think in the same terms as we did right here. When we were devising the series Bn, we were looking at the most important parts in the numerator. We're going to do the same thing. It's n cubed, but this time it's the coefficient that matters, coefficient of 2. There's a tie here, so in the bottom we grab the coefficient of 1. And now this rational function in the variable n, it has a horizontal asymptote, 2 over 1, which means the limit's 2. It's greater than 0. Double check your summary of tests. That's what we were going for, a limit that came out positive. Now we can give our conclusion and say, this shows summation an converges. Now, that means right up here, we use the absolute convergence test. We ran through 2 other tests, limit comparison and p-series, but now we're saying summation absolute value of an converges. Here's our overall conclusion. We can now say, therefore, an, that's the original series now. Let's write it out just to be specific. So we go from -1 power of n, 2n minus 1, n cubed minus 3n. This converges absolutely. It's a lot of work, but we have a conclusion. Lots we could say about this conclusion, but any questions or comments first? Okay, maybe just some last parting thoughts on this. You might have noticed as we went through these results, we're making a big deal out of these statements right here. You can start with either the test for absolute convergence, or you could go with a different test, say, seeing if it's an alternating series and if it converges or not. And it's really hard to give advice on what to do each and every time, because on this problem, you really did need to do both tests. So we had to do the alternating series. But on our last part, if you think about our work, we really didn't need to do the alternating series test. Sure, it wasn't too many steps, so it's not a lot of work lost. But if you had an inclination that this converged absolutely, you could have just started at that test, and that's the only work that you would have had to have done. Let's make that a comment here, just to convey that last thought. If we suspect summation an converges absolutely, I can't say must because, I mean, must is not the right word there. You don't have to take these steps, but we should start with absolute convergence test, because that's the only test you really need to use if it does converge absolutely. If it doesn't converge absolutely, you probably have to show that and use multiple tests, like on our first example in example 3. But it looks like we did it, folks. I can't scroll down any further, so this is finally on page 7, the last part of the notes. Any questions at all before we take a look at the next section? Okay, let me close this up. And the next section, it's a little bit lighter than what we just got through. What makes 11.5 hard is not the fact that there's alternating series there. It's about absolute convergence. Whenever that test is used, a whole bunch of tests sometimes do get involved, making that a tricky section. 11.6, though, is kind of nice in a way. We're going to look at some really complicated tests, the ratio tests and the root tests. They're going to be very common tests when we are looking into power series representation of functions. So the way these tests go is they're about determining absolute convergence. That's kind of a nice thought already, because we know from our last 3 examples that we did today, determining absolute convergence versus conditional convergence, it is sometimes pretty tough. But then here comes the ratio test. The way our author proves that the ratio test is valid is they compare the ratio of successive terms right here in the original series with a comparison test. They compare it against a geometric series. So they're using our other tests to come up with brand new tests. That's kind of interesting in a way. Now here's how the ratio test goes. There are 3 outcomes. One of them is not a good one. Outcome 1, if you take a limit of the absolute values of your successful ratio of terms, and the limit is less than 1, then the series is absolutely convergent, which means it's convergent on its own, but that's the stronger statement. If the limit comes out as positive 1 for the ratio of successive terms, well, that means that the terms are actually not shrinking down to 0 very fast. This ratio being larger than 1 is signifying divergence. And so we have divergence in that case. And if the limit doesn't exist, but it's in positive infinity, it's still divergence. So you can't have an infinity on this one and give that same conclusion. So that means absolute convergence occurs when that happens. That's like the best case outcome. In the ratio test, your limit L is less than 1. If it comes out exactly 1, this is where we have problems. The test is inconclusive. Prior editions of the book, our author said the test fails, but I notice he likes to say inconclusive now. That's a good thing to say, because inconclusive means the test can't be applied to your particular series. It's either going to converge or diverge. You now need a different test. Our author gives some advice on when this happens a lot. Ratio test being inconclusive happens with p-series. That means you can't use p-series at all and run it through the ratio test. You're not going to get any good conclusion there, but you wouldn't want to anyway. The p-series test on its own is extremely fast. But it's good to know that there's a whole class of series where you can't even use this test in the first place. So when do you want to use it? You want to use this kind of test whenever you have something kind of weird going on. Like in this series, the 2 to the n part feels like a geometric series. The n squared plus 1 part in the numerator is a rational function. It might feel a little bit like a p-series, but it's also alternating at the same time. We could analyze this problem like we did before, but it's going to involve a lot of ingenuity because of the numerator being a polynomial, denominator being an exponential. So this test is really great when there's a lot of weird things going on in your series and you just can't categorize it. Here's how it goes. we have to take the ratio of an plus 1 divided by an. So it's not a bad idea to just be specific first time you're doing this. An is negative 1 power of n squared plus 1 over 2 to the power of n. An plus 1, we won't write this out each and every time, but for your first run through the ratio test, it's not a bad idea. Here's the successive term, an plus 1. It would be negative 1 power n plus 1, n plus 1 squared plus 1. That came from this portion right here. And from here, it will be 2 to the power n plus 1. So with those two written out, the test is now really rapid. Ratio test says take the limit as n goes to infinity of the absolute values of the successive terms, in this ratio, an plus 1 divided by an. It's always specific in this direction. The next term is always in the numerator. The prior term is in the denominator. So let's color code this out just to show how it's coming together in the algebra. We're taking that and just writing it in with absolute values. So limit n goes off to infinity, absolute value of negative 1 power n plus 1, n plus 1 squared plus 1. It's not a bad idea to do a little simplification. 2 to the power of n plus 1 is the same as 2 times 2 to the power of n. So that helps out down the line. We're divided by an. So here's where an is. That just means we're multiplying by the reciprocal of an. Kind of how we would in, say, like the limit comparison test. So this saves a lot of time just putting in the reciprocal, because you can imagine how long your notes would get and how tired your hand would be. We went like this and put stuff down below there. New step is to write out the whole thing where we multiply by the reciprocal, not making too much progress. So this is a shortcut that's practically just essential. Take this and form its reciprocal. 2 to the power of n, negative 1 power of n, and squared plus 1. And that saves a lot of time. At this stage, all we need to now do is start simplifying our results. Keep in mind, less than 1 is convergence, greater than 1 or infinity is divergence. Now we're trying to avoid that outcome. Equals 1 means we shouldn't have used the test in the first place. That's going to be a rare outcome in these notes because you're being asked to do questions where the test applies in the first place. Well, back here, we need to take that limit, and that looks like just a punishment almost, but it's really not that bad. We just have to see which parts get eliminated. For example, due to the absolute values, alternating portions are just gone. Because of the prior factoring right here, 2 to the power of n cancels with that 2 to the power of n, so we're left with a 2 down below. In fact, we can even move that in front of the limit. Say it's 1/2. Limit as n goes to infinity. There's no absolute values any longer because as n goes to infinity, anything involving n any longer are just positive values. So this turns into n plus 1 squared plus 1 divided by n squared plus 1. That's a limit we can do immediately. But if it helps, you could do a little bit further work on this. You could write this out as 1/2. Limit as n goes to infinity. Imagine expanding out to where the red dot is. You would get n squared plus 2n plus 1, and then plus 1 comes from the plus 1 way over here, over n squared plus 1. But then from this point on, we have a rational function in the variable n. You probably know what's coming. We look to certain coefficients. In front of this n squared is a times 1, and times 1 here as well. And we're going to take that coefficient and that coefficient, form a fraction. It's kind of a weird step to take, but just for emphasis on the notes, the work looks like this. Uh-oh, I did miss something. I forgot the 1/2 right there. That was making me a little bit nervous because if I forget the 1/2 and I get a limit of 1, I might think I'm in this realm, and that's not what's happening in this problem. It really has a good conclusion. So let me back off a little bit. take this 1/2 and put it out in front. It's going to multiply the value of this limit, which is the ratio now 1/1. So that means the limit came out as 1/2. Sigh of relief. That means we're in this land. The limit is less than 1. Our conclusion is absolute convergence. Let's just say that are our last steps. Less than 1. Oh, hang on, you actually can't write if I'm in an equation field. That's kind of weird. Less than 1. Let's highlight that right there. This implies our original series. Summation AN is absolutely convergent by ratio test. So we did it, folks. This one converges by the ratio test, and we might have suspected it should converge because a degree 2 polynomial doesn't really grow as fast when it's compared to a full-on exponential function. So really the convergence of this one had a lot to do with 2 to the power of n on this. But if you compare the work that we just did on the very last notes, even the very last problem, that was a lot of work. And here's the mathematical miracle. It's not always a big slog because the ratio test and the root test make certain series just very, very easy to navigate through. Sure, it's a lot of writing, but it's a very fast process in comparison. Any other questions, folks, on working through ratio test here? Okay, let's try out another one just for the sake of getting more practice. This is a good case for ratio test, a mixture of a polynomial and an exponential function. Another really good one for the ratio test is anything involving a factorial. Let's say that because that's almost a more important statement. A factorial is a very large red flag we need ratio test. So that alone again is my big indicator. So running through the ratio test on this one, not too bad, but we might need another page. Let's push this down to the next set. And let's start like we did before. Let's indicate first AN. AN is n factorial, divide by 7 to the power of n. Next, we need the successive term, the one right after, AN plus 1. The way we work this is, if it's a subscript n plus 1, then everywhere you see an n in the problem, we're just overriding with n plus 1. That means the numerator is now n plus 1 factorial. The denominator is 7 to the power n plus 1. This is a good time to review the factorial function. We had to deal with it a little bit in section 11.1 because we're dealing with taking limits involving this for sequences. But here's a quick rundown. If you have something like n factorial, it means you're taking n times n minus 1 times n minus 2, and so on until you get to 3 times 2 times 1. So for example, 3 factorial is 3 times 2 times 1, which is equals 6. One thing that's kind of curious about the factorial function that always bugged me is we always put that times 1 there. It doesn't affect the product at all. You get the same answer if you forgot it. That's just kind of a reminder. If you say 3 factorial, you're expecting 3 factors. It's really the only reason we do that. What we need in our problem, though, is if you have something like this next, say it's n plus 1 factorial. You can rewrite that too. It could be n plus 1 times n minus 1 times n minus 2, to say, and so on, 3 times 2 times 1. But then if you're looking at that part is all of this. It's just another way, once again, to say n factorial. So what this implies is, if an n plus 1 factorial comes up, probably the best thing you ought to do with that is take n plus 1 factorial, write it as an n plus one. All of that is n factorial, so we'll write that part in as n factorial. And that gives us a great simplification on our next steps. So really the major work on this problem is just the early analysis, deciding what to do with the factorial. At this stage, we're ready to throw it all together, take the limit. Any questions at the moment first? Okay, so here's how it goes. Limit as n goes off to infinity of the absolute value of the n plus 1th term divided by the nth term comes out like this. It's the limit as n goes to infinity. And maybe one thing that's kind of interesting to observe is absolute values serve no purpose at all in this problem. I just wrote it down because that's the pattern in the ratio test. But all this is always positive. And that's okay. You can use this even if the terms are alternating, not alternating, ratio test still applies. So it's the limit as n goes to infinity. We're just dropping absolute values right away and putting in a n plus 1. So that's the n plus 1 factorial. We'll rewrite it as n plus 1 times n factorial. And while we're doing that, we should rewrite the exponential as 7 times 7 power n. Then we multiply by the reciprocal of this nth term, 7 power of n divided by n factorial. The limit still looks pretty nasty, but this is the experience. When you're using the ratio test, there are always major cancellations, which suddenly make the limit approachable. A factorial is gone, for example. 7 power of n is eliminated. And all we're left with is limit as n goes to infinity, n plus 1 divided by 7. Any volunteers for what that limit should come out as? I think this one's tricky based off what we've done so far today. It is infinity, good call. This time the denominator is constant, but as n goes to infinity, so does that n right there, and your numerator just gets larger and larger and larger without bound. The whole thing comes out as infinity. That is sometimes a major concern, actually. Imagine, for an example, you're doing the limit comparison test. We never want to see an infinity on that because you want a limit that's C, that's positive and not infinity. It has to be an actual number. The ratio test doesn't care. If your limit comes out larger than 1, or if it comes out as infinity, we have a conclusion of divergence on this one. So we'll say here, diverges by ratio test. So that series right there, it's really nasty and complicated to do without the ratio test. It could take a lot of ingenuity. I might have to do some kind of weird comparison test, but the ratio test is fast and immediate. So it's a great one to add to our arsenal. What we did, folks, those are two pretty interesting series, not easy to test without our brand new tools. And let's see, we've got about 9 minutes. You know what? 9 minutes is enough time to do one more. So let's do one more for the road, and then we'll call it a night. We're just going over to next, the root test. After doing the ratio test, this is not too unfamiliar in a certain sense. The reason it's called the root test is because we're taking the limit as n goes to infinity of the nth root of the absolute value of the nth term. But looking at these tests, here's the nice thing that I like about ratio test and root tests. The form changes. You have a ratio versus a root, so we expect that. But the thing that's consistent, wonderfully consistent, is the conclusions are all identical. Less than 1 is convergence in either case. Greater than 1 or infinity is divergence in either case. And it fails in the same cases as well, whenever the limit comes out as a 1. It's nice to have a little bit of consistency there. So only thing different is just the form it takes. So it's essentially the same example, same instructions, but this time we're using the root test. What's the giveaway? That we need that root test? It's anything that looks like that. we have what would be an interesting series already on its own. But we're taking that whole -2n, n+1, and raising it to a power. So that right there signifies ratio test is effective. So if the ratio test is effective, we might want to do a little bit of further work on this thing. Let's say in this problem, an is, well, there's a lot of stuff going on. We have something raised to a 5th power and then an nth power. But we can break this up as -2n divided by n+1 to the 5th power, put a bracket on that, and raise the whole result to the nth power. It's kind of ugly to look at, and it's not a totally required step, but it could help out algebraically with what we're about to do here. It's a reminder when we go to take the nth root, the only thing that's canceling off is that power n, and 5 is going to survive. So let's write this out. The limit as n goes to infinity of the nth root of the absolute value of an is now the limit as n goes to infinity. Let's make this a really large nth root. If you like, by the way, you can write your nth root like this, just a big parenthesis with a power of 1 over n, if that just seems like a good stylistic choice. In place of that, I'll just write out the way our author usually does. For an, we're plugging this in, but we're also taking the absolute value of it. So it's going to be, let's see, how should we write this? Absolute value -2n, n+1 to the 5th power, raised to the nth power, close absolute value bars. That's almost kind of dizzying to our eyes, but let's see if we can help that out a little bit better. Let me just give the absolute value bar a color so it doesn't look like we're trying to hypnotize ourselves or something. So this configuration, the major reason we use the root test is because this nth root cancels that nth power. So we're left with just the absolute value of all of this to the 5th power. We can maneuver through that. Let's say that the limit is next. As n goes to infinity, the absolute values is going to eliminate the negative sign on this, and now it's just 2 power of n. Divide by n+1, still to the 5th power. The 5th power still surviving is a bit pesky, but a function like that is continuous. So we can say it's the same as this as a 5th power. The limit operator goes inside the function, and we are taking the limit as n goes off to infinity of 2n divided by n+1. Let's throw a 1 in there. This rational function has a tie in degree with numerator and denominator, so the value of the limit is just 2 over 1, raised to the 5th power. So we get to the 5th power, there it is, that comes out as a 32, which is greater than 1. Now, conclusions always go the same here. Greater than 1, either finite or if we got infinity, it's divergent by the root test. So we'll say here, because of this portion diverges by root test. So again, that's another extremely hard series to test. I have to be honest with you, without the root test, I really don't know how I would test that series. That's weird enough with that outer power here to really, you'd have to come up with something very, very ad hoc and ingenious, I'd say. But the ratio test doesn't care. It's going to eliminate that power n, and now the conclusion is immediate. This is another good one, but it requires a little bit of work on exponents before we can get started on it. So it seems like a great one when we come back to class on Wednesday. We'll also take a look at some summary problems here on example 3, where it's now just some few random series. We have to decide what's going to work on this stuff. Then from there, we're going to be taking a look at power series starting in Wednesday's class. So that'll be exciting. Well, any last questions at all, folks, before we call it a night? Okay, well, drive safe, everyone. Hopefully it's not snowing out there. Been afraid to look. And I'll see you all on Wednesday.